Assalamualaikum and greetings to fellow examiners. My name is Hidayah Binti Hamzah and I am supervised by Dr. Arzanti Binti Saroni. I will be presenting about a review on variation growth approach of indium tin oxide, this is my final year project title. This is the overview for my presentation today. A review of the growth effect of ITO was conducted by comparing various techniques of growing the ITO in the industry. The objective of these investigations is to see how different growth methodologies and mechanisms via pulse laser deposition, ion beam assisted deposition, thermochemical fiber deposition, this is part 3, and electron beam deposition affect the structures of indium tin oxide. The findings indicate the simplest option for analyzing the growth effect of indium tin oxide nanostructures based on the level of production of ITO. Above all else, the results of this review highlighted the significance of the growth method used to produce ITO, not limited with improved quality, structure, and its properties, but also the functionality due to the modification on its structure. The development of more advanced electronic systems and producing semiconductor metal-based nanowires and nanorods is critical nowadays, which can enhance the electronic and optical properties to a broad array of applications from photovoltaics to sensors. Furthermore, ITO acts as a translucent conductive material when placed as a thin coating on glasses or transparent plastics and generally marketed as a powder, but it can also be obtained as the ITO targets for sputtering or ITO chunks for thermal evaporation and being used in a new generation of solar cells, which is an exciting new application. ITO nanostructures have a better surface to volume ratio and crystallinity than polycrystalline films. Yu and Lee 2014 stated that ITO has maintained as one of the most significant transparent conducting materials due to its particular transparency and conductivity properties. Thus, it will be extensively used in the optoelectronic industry. Some of these approaches, such as thermal treatment, require a high growth temperature and would thus be unsuitable for development on the glass substrates, which are contradict for a low-cost optoelectronic device applications. ITO, also known as brittle material. Low-temperature techniques, such as chemical synthesis, on the other hand, produce freestanding nanostructures rather than nanowire arrays or networks on the substrate. The low crystallinity of indium tin oxide film has a negative impact on the device critical characteristics, such as driving ability and optical parameters. Besides, the internal tension between layers of various materials always develops during the process of temperature rise and fall due to the mismatch or the thermal expansion coefficient between the substrate material and the conductive film. Due to their high porosity, indium tin oxide nanostructures are ideal candidates for transparent conductive oxide applications such as optoelectronic electrodes, and this study can greatly contribute to more research on them. The growing effect of ITO nanostructures was examined in this recent work. This research focused on the numerous methodologies used to investigate the impact of indium tin oxide on growth and to identify the best accountable mechanism for indium tin oxide. This knowledge will aid in balancing structural and conductivity requirements in transparent conductive oxide network applications. The purpose of this research is to examine how the characteristics and structures of ITO nanostructures are affected by varied growth techniques and mechanisms. Next, to study the growth impact of ITO nanostructures and to determine the most effective way for analyzing the growth effect of ITO nanostructures. The method used to grow the ITO. This figure represents PLD method that shows the growth nanowires only exhibited the rutile crystal phase without the significant indium component when the total material flux relatively low was used, as indicated in figure A. The fabricated nanowires show the metastable fluoride crystal phase when the material flux was raised up to 6 times 10 to the power 17 cm-2 second-1. The produced nanowires seem to be of bits byte crystal phase of the standard SN doped ITO as the material flux further increased, as illustrated in figure C. According to these results, material flux greatly influenced the crystal phase of growth nanowires, even though utilizing the conventional experimental configurations of vapor-liquid-solid nanowire growths. Next, the figure explained that the tin concentration was nearly 100% with the rutile crystal phase of stannic dioxide as the material flux below 4 times to 10 to the power 70 cm-2 seconds-1. However, the tin concentration was around 30% with the fluoride crystal phase of metastable ISO when middle material flux range of 6 to 14 times 10 to the power 17 cm-2 seconds-1 was used. The tin concentration dropped to roughly 20% with the bits byte crystal phase of ITO for the higher material flux range. Meng et al. 2014 suggested that the crystal phase of nanowires generated was controlled by material flux during the vapor-liquid-solid nanowire growth of indium tin oxide. IBAD transformed the randomly oriented branch-type nanowires to align nanowires with no branches throughout electron beam evaporation process due to the high-level energy ion beams that help to nucleate tin-containing indium nanodotes at the beginning of the growth process. The source material is a tin dope and indium oxide pellet with a purity of 99.99%. We can see at a rate of 0.5 nanometer seconds, -1, ITO nanowires were grown. To form well-developed ITO nanowires, the chamber pressure was maintained at approximately 10 to the power of -5 torr, and the substrate temperature was maintained at 300 degrees Celsius during the deposition process. In addition, nitrogen gas was flowed into the chamber at a pressure of 0.2 meter torr. We can see that as the ion beam voltage increased from 50 volt to 150 volt, the branch-type ITO nanowires gradually vanish. Next, the figure shows a branch-type ITO nanowires grown with time 20, 80, and 300 seconds under normal electron beam evaporation conditions. The VLS process was begun by the metally INSN nanodotes shown in the 20-second growth image, which resulted in ITO nanowires. Additional nucleation of INSN nanodotes on the 100 family plane of the Bits-Biat ITO crystal resulted in the development of ITO branches. Nonetheless, the development of ITO nanowires growth with and without IBAD differed significantly. IBAD inhibited the nucleation of INSN nanodotes because the intense ion beam blocked other atoms, notably SN, from migrating. By lowering the melting temperature of the alloy, this obstruction aided in the accretion of nanodotes. The ion beam prevented the nucleation of additional alloy nanodotes on the ITO 100 family plane, resulting in nanowires with no branches as shown in the 300 seconds growth image. This figure represents the ITO growth by CVD. After which 900 degrees Celsius, the nanostructure was grown on the substrate for 20 seconds as shown in figure A. We can see that a rough discontinuous buff layer of crawling nanowires are formed and droplets that serve as catalysts develop at the nanowires ends. Moreover, the crawling growth mode of the nanowires on the surface shifts to vertical growth mode after 30 seconds of growth time. Regardless of the droplet size, the head separates from the substrate occurred in figure B. The nanowires form a branch structure after 20 minutes of growth, as seen in figure C. ITO nanowires produced are shown in the first two figures, which A is on glass, B on ITO glass. From this spectrum, nanowires grown on glass are longer than those on ITO glass substrates, which approximately is 5 micrometer. In comparison of the nanowires, the tips of nanowires produced on titanium show a greater narrowing near the nanowires tip. Compared to titanium substrate, branching structures appear to be more prevalent on ITO titanium substrate. The morphologies on the silicon 100 substrate are different as seen in the last figure. The ITO film has square grains as well, but less coarse than the film on titanium foil. According to the figure, short rods with high diameters are generated instead of lengthy nanowires on both silicon and ITO silicon. This is most likely owing to variations in nucleation and surface migration rates on different substrates. The figure shows the process of e-beam deposition. This approach uses polystyrene as a catalyst and operates at a low temperature to produce ITO nanowires. Figure B shows the PS spheres were then etched for 200 seconds with oxygen plasma to change their shape and lower their diameter while increasing the spacing between them. Next, ITO source was deposited on the template by electron beam evaporation for 15 to 20 minutes at a deposition rate of 0.1 nanometer per square with the chamber temperature stabilized in C. Finally, the PS material was removed by annealing under nitrogen conditions. As a result, the ITO nanowires were grown purely as illustrated in D. Figure on the above shows a standard ITO film placed on the surface without PS spheres, which no nanowires on the substrate can be seen. The one with the PS sphere shown in B is deposited with ITO under the similar conditions where the ITO nanowires have been produced. It implies that the polystyrene catalyst is important for the production of ITO nanowires. In addition, during the ITO deposition process, the PS spheres begin to melt in the chamber at temperature of 300 degrees Celsius. Figure C shows the shape of ITO nanowires after the PS was removed by annealing. The formed ITO nanowires are compactly knitted, and the morphology of the ITO nanowires has not changed after the PS spheres were removed. In the absence of PS spheres as a catalyst, some ITO molecules are absorbed and clumped together on the substrate, while others are bounced back, as illustrated in D. The figure below is the image of ITO nanowires prepared by PS spheres from 5 to 20 minutes with the same size diameter of PS spheres. Next, the structure properties of ITO are characterized by X-ray diffraction, which is material science method for identifying a material's crystallographic structure, and high-resolution transmission electron microscopy. And the last one is selected area electron diffraction, known as crystallographic experiment, that is commonly carried out with TEM to analyze the electron diffraction pattern produced by the electron beam's interaction with the sample atoms in order to assess the sample's crystallinity, lattice parameters, crystal structure, and also the orientation. The XRD patterns of ITO nanowires grown for 20 minutes with and without the presence of oxygen gas are shown in the figure above. For the nanowires growth without oxygen gas flow, sharp diffraction peak mainly attributed to cubic structure of ITO. But for the nanowires grown with the presence of oxygen, diffraction peaks typically correlate to cubic structure ITO only. This is because of oxygen functions as a source for oxide nanowire formation. As a result, nanowires generated in the presence of gas flow are longer than those formed in the absence of oxygen flow. For the third figure, the peaks of ITO nanowires are quite visible as compared to ITO film, implying that the ITO nanowires are closer to an integral cubic lattice. We can see the XRD peak is at 2 theta equals to 35 degree. Meanwhile, for the second figure, the XRD peak is at 2 theta equals to 27 degree for stannic dioxide and approximately 30 degree for ITO. For the first figure, for 222, the XRD peak is at 30.5 degree and 35.4 degree for 400 peak. The figure represents HRTM image on the surface of the stems. Branching nanowires develop epitaxially. Metallic SN droplets grow on the main stems, while smaller droplets formed by evaporated crucible vapors can form on the side wall of the main stems at the same time. As a result of this, branch nanowires were formed as shown in above figure. The HRTM image in figure below clearly indicates the high degree of crystallinity as well as the presence of distinct lattice fringe. The INSN alloy and the nanowires were coated with PS at the start of the nanowires development process shown in the figure above. The alloy particles were attempting to break free from the shackles of PS by continuously drawing nanowires. We can see that the lattice spacings for alloy is 0.25 nanometers. HRTM image of the crawling nanowire, which were grown for 20 seconds, are shown in the figure at the below. For plane 101, 121, and 011, the lattice spacings are 0.28 nanometers, 0.148 nanometers, and 0.253 nanometers respectively. 0.25 nanometer lattice spacing corresponds to 004 plane. Due to the obvious diffusion of SN into the ITO lattice and the Due to the obvious diffusion of SN into the ITO lattice and the resulting reduction in lattice spacing, the nanowires lattice spacing is slightly less than the standard value, which is 0.253 nanometers. As mentioned by Ding et al. 2006, the growth along the 100 axis is faster than growth along the 222 axis, which development of nanostructures along the 100 axis is expected. For the second figure, the branching nanowires develops epitaxially on the stems. The branches are single crystalline as well, with the same lattice spacings and diffraction patterns as the backbone of the nanowire. From the figure, electron diffraction analysis along the 001 and 011 axes showed the presence of the fluoride phase. It indicates the fundamental methods by which the material flow impacts the indium tin oxide nanowires crystal phase during VLS growth. To add on, when indium and tin elements are present in the metal catalyst, a variety of indium, tin, and oxygen-containing crystal phase can develop at the LS interface. In conclusion, the oxygen molecule on ITO nanobranches has several vibration routes in the potential wall, whereas the oxygen molecule on IBAD ITO nanorods exhibits only a few vibrations. As a result, the reasons for the fast response time in IBAD ITO nanorods might be explained as follows: rapid translation of the gas molecule without various simultaneous scattering in the nanostructure matrix due to alignment, and quick chemisorption of oxygen gas due to the high friction coming from surface floors. Next, the initial stages of nanowire growth by CVD technique demonstrate that crawling nanowires form from the SN liquid droplet and keep growing by pushing the SN droplet along the Si surface. This proves that oxygen inhibits the droplets from re-evaporating, leading to longer nanowires than those that were produced in the absence of oxygen flow. Moreover, the sheet resistance of the nanowires formed on ITO film by DC sputtering was 8 ohms per square, demonstrating the nanowires' good electrical characteristics. In addition, the advantages of using PS spheres rather than metal catalysts in E-beam are inexpensive cost, simple removal, and low deposition temperature needed. The ITO nanowires that are manufactured have improved crystallinity and a propensity to orient vertically, which makes it perfect for improving light extraction in LEDs. Based on the results of this study, the electron beam deposition and ion beam assisted deposition method are suggested for producing ITO nanowires that are higher quality in terms of their structure, their characteristics, and their usefulness in industry, especially for electrical applications. This is the list of reference for my review article. That is all. Thank you for listening.